Okay, so what we're going to talk about today is graphing polynomial functions, and this is one of my favorite topics to teach or sections to teach, just because we can have this really ugly looking polynomial function and yet we'll be able to graph it without using a graphing calculator. So I know that you did some of this last year, so hopefully this stuff isn't anything new to you. So, but we will start from scratch anyway. So let's start off by defining what a polynomial functions are. Okay, so we would say that a polynomial function of degree n is a function of the form f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus all the way until we reach our constant. So just keep in mind that this is like a generic description of a polynomial function, but if our degree is n, that has to be the largest degree, and then as we go along, each variable loses a degree by 1, right? And then these a sub n minus 1, a sub 1, a sub 0, those are just going to be constants, right? So for example, if this degree doesn't belong here, then this will be a 0, and then it'll 0 it out, okay? So we would say where n is a non-negative integer. So this is crucial because for us to have functions, what we're saying is all the variables must have integer exponents, and a sub n doesn't equal to 0. And the reason why we don't want a sub n to be 0, because if a sub n is 0, then this function will no longer have a degree of n, it'll have a degree of n minus 1. Just to stay consistent with that, remember the highest exponent in your polynomial function, that's what the degree is, okay? So let's also talk about the numbers a sub n minus 1. I just mentioned it, but let's put it in our notes. So the numbers a sub 0, a sub 1, all the way to a sub n, these are called the coefficients of the polynomial. Okay, so those are the coefficients of the polynomial, which they're just the constants in front of your variables, okay, with a sub 0, which is this guy. And notice how that doesn't have a variable, right, because it doesn't have an x, which that's known as the constant coefficient. And a sub n is the coefficient of the highest power. And also known as, so we can put aka, the leading coefficient. And then one last term I want to mention here is the entire first term, right? See a sub n x to the power of n. This is the leading term. Okay, so before we get into the more complicated polynomial function, let's talk about our basic polynomial functions. So our basic polynomial functions and we're going to talk about of the form, just the most basic polynomial, which would be f of x equals x to the power of n, right? So notice how this is still a polynomial function because it fits the definition, but it's pretty much the most basic one we'll see, where it's x, just a single term. So our attention is going to be, well, what happens when n increases? How do they behave, or how does the graph look? So there's two parts I'm going to break this up to. I'm going to say, well, what if n is an odd power, and then what if n is an even power? Okay, and then we can go from there and see exactly how they change. So if n is odd, so here's what we have. Let's kind of see what happens to the cases. So if n is 1, what happens? That just becomes x to the power of 1, which is just x. That's a line. So it looks like this. So that's 1, 1, negative 1, negative 1, right? So that's kind of what it looks like. Now, what if n is 3? Now, we know what this looks like. This becomes x to the right. We're talking about x cubed. That's what we're saying. So we know what the graph of this looks like, because at 1, it's 1. At 0, it's 0. At negative 1, it's negative 1. And we know it has this shape. Okay? Now, here's what I want to point out. If n is 5, which would be, this would be x to the power of 5, the graph of x to the power of 5 is identical to x to the power of 3, except for one comment I want to make here. Between 0, see, notice how at x is 0, it'll be still 0. At x is 1, it'll still be 1. At x is negative 1, it'll still be negative 1. However, between 0 and 1, this is going to be flatter. It's going to stay closer to 0 than that one is. How come? Because when you take a higher exponent and you plug in a number between 0 and 1, it's going to be closer to 0. So for example, if I plug in 1/2 for x cubed, what do I get? I get 1 over 8. But if I plug in 1/2 for x to the 5th, what do I get? I get 1 over 32, which, notice, it's causing it, it's kind of pushing down on it. And then what do we notice? After 1, x to the power of 5 will increase faster than x to the power of 3, and it'll decrease faster. So notice how this looks like that, except between 0 and 1, it looks flatter, and then after 1 and negative 1, it increases and decreases faster, but the shape looks identical. Now, by using that reasoning, what do you think would happen if n is 7? Well, same thing, right? At 1, it'll still be 1. At negative 1, it'll still be negative 1. At 0, it'll be 0, except between 0 and 1, x to the power of 7 will be even flatter than x to the power of 5. So it'll be flatter, and then it'll increase even faster. And then it'll be flatter even more, and it'll decrease even faster. So what we're basically saying is, if the power is odd, and as it increases, the y values between 0 and 1 will become flatter, or will stay closer to 0. And then after 1 and negative 1, it'll start increasing and decreasing much faster. But hopefully you see how the shape stays more or less the same. Okay? Now, what if n is even? Same idea is going to happen, except you'll notice how except they're all going to look like parabolas. So if n is 2, what is it that we're going to have? We're going to have f of x equals x squared. So same reasoning. At 0 it'll be 0, 1 it'll be 1, negative 1 it'll be 1, and it looks like this. What if n is 4? Now we're talking about x to the power of 4. So if it's x to the power of 4, notice how at 1 it'll still be 1, at 0 it'll be 0, at negative 1 it'll be 1. But how is this going to be different than that? Same reasoning. Between 0 and 1, it's going to be flatter. After 1, it's going to increase faster. Same thing. Between negative 1 and 1, it's going to be... So when I compare this to that, it looks flatter and it increases faster. What if we take n equals 6, which means we're talking about f of x equals x to the power of 6. Once again, between... So the 0, 0, 1, 1, negative 1, 1 will all be the same. But between 0 and 1, it'll be, negative 1 and 1, it'll be even flatter than x to the 4th. And then after negative 1 and 1, it'll increase even faster. So it might look something like that. So we start seeing that as the exponent increases, same thing happens here. So let's look at our first example, where we're going to say sketch the graph of f of x equals to x plus 1 to the power of 5. Okay, so I'm going to use transformations because to me transformations are the easiest way to go about it. So what do I know? The basic function I'm going to start off with is what, x to the power of 5. So what do I know about this? It's going to look identical to x cubed, except it's just going to be a little flatter. So it's kind of going to be like that, right? So it's just flatter than x cubed, and it decreases and increases faster. Okay, so now the x plus 1 is saying what? Shift it 1 unit to the left. So it'll be here, here, and here. So it'll still be the same, it'll still have the same flatness. So it's kind of like I grabbed that guy and moved it 1 unit to the left. Okay, so that takes care of our basic polynomial function. So now the next thing we want to talk about is the end behavior. So what is the end behavior? It's literally kind of what we care about as far as at the ends. What does the graph do when we go towards infinity and negative infinity? That's what the end behavior is. So let's kind of describe that here. So the end behavior behavior's purpose is to determine what the polynomial function behaves like as x becomes sufficiently large and small. So in other words, we're saying, what if my x values go towards infinity and negative infinity? So there's kind of like a way I want to, and the way we're going to focus on this, here's what we're going to say. Here's how we're going to know what the end behavior is. For any polynomial function f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way to a sub 1x plus a sub 0. We care about the leading term, and we focus on the degree, actually, to be honest with you. So for the end behavior, only focus on the leading term and the degree of the leading term. Why? Because for really, really large numbers, the expression with the highest degree is going to start determining what happens, if it's going to be positive or negative. So this is what we care about. Okay, so we would say, look, if the degree is even, and so we're looking at the degree, if that degree is even, and then we look at the coefficient, and the leading coefficient is positive, then my end behavior is going to look like this. So we're not saying we know what it's going to do in between. We'll talk about that in a moment. But I know towards the end, we know that this graph is eventually going to go up forever in both sides. Okay? So what if the leading coefficient is less than 0? If it's even and the leading coefficient is less than 0, then it's going to go down from both ends whenever you go to the end. Okay? Then, what if the degree is odd? So notice how this behaves like our x to the second, x to the fourth. That's kind of what it looks like, right? So then, if the degree is odd and the leading coefficient is positive, then my end behavior, as I go to the right, is going to go up forever. As I go to the left, it's going to go down forever. And then we could see that if the leading coefficient is negative, then it's going to be flipped. So to the right, it's going to go down forever. to the left is going to go up forever. So you're going to notice, you might be wondering, why do we care about this? Well, eventually when we graph polynomial functions, it's nice to know the end behavior, because if I know the end behavior, then I know exactly what it's going to look like once I take care of the in-between stuff, right? So it gives us more information regarding the graph. Okay, so let's look at our second example. So for example 2, determine the end behavior of f of x equals to negative 3x cubed plus 20x squared plus 60x plus 2 using arrow notation. Okay, I'll show you what it means to use arrow notation in a minute, but let's look at our function. What's the highest degree of this? Is 3. So my leading variable, or the leading or the degree of this polynomial is 3. And then we say, so we know it either goes up on one side down, or vice versa, down then, or up then down. So what tells me what this is? If I look at the coefficient, it's negative. So since the degree is odd, this is negative. We know the end behavior is gonna look like that. So let's use arrow notation. So what do we notice? This is what arrow notation is. As x goes to infinity, what does that mean? As x gets really, really large, what do you notice the function does? F of x goes to negative infinity, which means it's going down forever. So then what happens as I move to the left? As x goes to negative infinity, what do we notice f of x does? F of x goes, or my function, or the y values, go up forever. So that's what they mean by end behavior using arrow notation. Okay, so the next thing we're going to talk about are the real zeros of a polynomial function. Okay, so the real zeros of a polynomial. And when we talk about real zeros, these are pretty much our x-intercepts. So we could see why we're breaking this up into pieces. Eventually we're going to put everything together. So here's what the real zeros of a polynomial are. So I'm going to kind of show you four different ways of looking at this. So if P is a polynomial, so I'm basically telling you that, hey, capital P, that's a polynomial function, and I tell you that C is a real number. So C is some constant, it's a real number. Then the following are equivalent. So these, I'm going to give you 4 comments, and these 4 comments they all mean the same thing. Or if one is true, then all the other ones are true. So the first comment is C is a zero of P. So what we're saying is, look, if C is a zero of P, in other words, if I plug in C into this polynomial function, I get 0 out of it. Then if that's true, then we could also say x equals C is a solution of the equation P of x equals to 0. And once again, what is it that we're saying x equals C is a solution? That means if you plug in C in for x, you get 0. So notice how literally we're saying the same thing as these guys. And then another statement that's true, x minus C is a factor of P of x. So what we're saying is, look, if C is a 0 of P, then that means I should be able to factor out an x minus C. In fact, if you think about when you guys solved functions, polynomial functions, and you found their zeros, what's one way of doing it? You try to factor it. And if C is a 0, then x minus C better be a factor of it. And then the fourth statement, which is equivalent, what do all these mean? What does it mean if c is a 0, if x equals c is a solution, x minus c is a factor? Graphically, we know that c is an x-intercept of the graph of P. So just real quick to make a comment here, and I'll come off to the side and make this. So for example, if we look at it, what do we have here? X squared minus 4 equals to 0. If I said, hey guys, find the zeros of this, what would you do? You'd say, look, this becomes x minus 2 times x plus 2, which equals to 0. Then what is it that we know? X equals 2 and x equals negative 2 are the solutions. Notice how this satisfies all four conditions. See, what do we know here? 2 and negative 2 are zeros of my function. Why? Because if I plug in 2 and negative 2 for x, I get 0. X equals c is the solution of the equation. So notice how 2 and negative 2 are solutions because that's what the zeros are. Obviously, x minus c and x minus c's are factors because if x equals 2 is a solution, x minus 2 is a factor, x plus 2 is a factor. So you could see how just this, all four statements are equally true here for that example. Okay, so the next thing we're going to talk about is something known as the intermediate value theorem. And this is going to be very, very important in calculus. So you'll see intermediate value theorem again in calculus. So this is for polynomials. In calculus we can say, hey, we can use it for other types of functions, but our focus is on polynomials. So we would say if P is a polynomial function and P of A and P of B have opposite signs, then there exists at least one value C between A and B for which P of C equals to 0. So the intermediate value theorem kind of guarantees, it doesn't tell us where the zeros are, but it guarantees that we have a 0 between A and B. So here's what they mean. Look, if I have A and B, right, that's what this is saying. And if I plug in A into my polynomial function, let's pretend it puts us up there, P of A. That's P of A. And then let's say P of B puts us down here because we're supposed to have what? Opposite signs. So P of A is positive, P of B is negative. And what we're saying is, and we know polynomial functions are always continuous, they don't have any cuts or breaks. So to go from A to B, and since P of A is a positive y value and P of B has a negative y value, I have to cross the x-axis at some point. So that's what they're calling C. They're saying, look, there's at least one place between A and B where this graph crosses the x-axis, which that's where my 0 is. Okay, so the intermediate value theorem kind of shows the existence of a 0. Okay, so moving on. So now we care about the shape of, oh, sorry, we have an example to do before we talk about the shape. So example 3, find the zeros of, and let's write these out. A is P of x equals to x cubed minus 9x squared plus 20x, and then B is P of x equals to 3x to the 4th minus 5x cubed plus 20x. Okay, so if we're finding the zeros of this, what do we need to do? I'm sure you've done this before. We take x cubed minus 9x squared plus 20x. We set it equal to 0, and then we solve this by factoring, right? So if I factor out an x from this, I get x squared minus 9x plus 20 equals to 0. And it looks like I could factor that further, which gives me x minus 5, x minus 4 equals to 0. So my zeros are what? X equals 0, x equals 5, x equals 4. Now, visually speaking, this is where the graph crosses the x-axis. So that's also important because eventually we're going to put everything we've learned together to graph a function. Okay, now this one you might want to pause the video and do this on your own and then press play, but we're going to do the same thing. We're going to set this equal to 0. We're going to solve by factoring. So if I factor out an x, what does that give me? This gives me 3x cubed minus 5x squared plus 20 equals 0. Oh, sorry, I wrote this incorrectly. This should be 3x to the fourth minus 5x cubed plus 12x squared. That's what this should be. Okay, so if I come back down to this, this should be 12x squared. So now I could actually factor out a what? I could factor out an x squared from this, which makes this 3x squared minus 5x plus 20. Now I wonder if this could be factored, because what do we have? We're going to have 3x and an x. And then what do I want? We want to get a negative 5x, which, and one other typo, this should be a minus, so these are all minuses. So then what is it that I need? I need negative 5. So once again, we probably want to go 5 and 4, but if I put the 4 here, does that work? Let's see. This would be 5. This would be a 4. No, that doesn't work. What if this is a 5? That's a 4. We get 3 times 4 is 12x minus 5x. That's 7x. No, and this doesn't seem, well then what would mean is that this one, if we can't factor it, would use the quadratic formula. So we would say, so the zeros for this is x equals to negative b, which is 5, plus or minus square root of b squared, which is 25, minus 4 times ac, so it's 3 times negative 20, all over 2a. Okay, so remember, if you can't factor and it's a quadratic, you could at the very least use the quadratic formula. And then what does this become? 25, that's what? 80 plus 3, 240, 265 over 6. Okay, and then I'll let you simplify this further, but there you have it. So we weren't able to cleanly factor that. Not a problem. We were able to do this. Okay, so now the next thing we're going to focus on is, well, the shape of the graph near a 0 of multiplicity m. Now the multiplicity is how many of the same 0 we have. So that is going to matter. That's going to make a difference. So if C is a 0 of P of multiplicity M, then if, so there's two cases, the question becomes, one, if M is even, the graph will bounces off the 0 and behaves like its power. So for this, what we're basically saying is, look, because whenever you have an x-intercept, the question is, hey, does the graph cross the x-axis or does it bounce off? Well, it depends on the multiplicity. So for example, if the multiplicity is 2, what is it that I know at C? it's going to come and bounce off, and it's going to act like a parabola, like the x squared. If the multiplicity is 4, at C, it's still going to act like a parabola, but what is it that we know? It's going to be a little flatter. It's going to act like the x to the 4th, okay? So, and you'll see, we will do an example in a minute where we will identify the multiplicity, and then we'll be able to kind of go further with that, okay? Now, what if m is odd? If m is odd, then the graph crosses, so this is where it's not going to bounce off, it's going to crosses the 0 and behaves like its power. So what do I mean? If the multiplicity is 1, I only have one of that factor, it's going to cross and behave like a line. It's going to be kind of linear. Where if the multiplicity is 3, at C, it's going to act more like a cubic, right? Kind of like our x cubed graph, right? That's what it acts like. So now, what we're going to do now is we're going to put everything we just talked about together, okay? So the next thing we're going to say is, well, what are the steps? So these are the steps to follow when graphing polynomial functions. And then we'll do a bunch of examples, and then that'll basically finish this off. So the first thing we want to do is find its y-intercepts, x-intercepts, and identify their multiplicity. And when I'm saying identify the multiplicity, I'm talking about the x-intercept, right? Because the x-intercepts are finding our zeros. Now, why do we care about the multiplicity? It's does it bounce off or cross, okay? The second thing you're going to do is identify the end behavior. Okay, so as you're identifying the end behavior, you're going to notice that that's kind of going to get us closer into graphing certain things here. Okay, so we identify the end behavior, and then the third step is not necessarily needed. We would say if, but there might be some cases where we don't have enough information. If needed, find additional points, but we don't care much for that, right? And then once you have all the information, you're going to put everything together and graph. Okay, so these are the steps we're going to follow. So let's start off with our next three. We're going to do a couple more examples, or maybe even 3, just to see how these work. So we're going to say graph p of x equals to x minus 1 squared, x minus 2, x minus 5 cubed. Okay, so the good news is this is already factored for us. Now, to find the y-intercept, that's very easy. All we have to do is set x equal to 0. And if I set x equal to 0, I get negative 1 squared times negative 2 times negative 5, which ends up being 10. That's my y-intercept. Now, for the x-intercept, since this is already factored for us, what do? We just, right, because we set this equal to 0, and if you remember, we would then try to factor, but this is already factored, so this is nice for us. So what's my first x-intercept? X equals to 1. Now, however, what's the multiplicity of this? Notice how many x minus 1s I have. I have 2 of them. So the multiplicity is 2. And then what's the next one? X minus 2, which that's x equals to 2. What's the multiplicity of this? I only have 1 of them. So that's multiplicity of 1. So we know that the graph is going to bounce off here, and it's going to look like a parabola. We know it's going to cross here, and it's going to look linear. And the last one is x equals 5 with a multiplicity of 3. Okay, so now what's the end behavior? Well, I don't care to multiply this out, but I know that if I multiply this whole thing out, what's my degree going to be? It's going to be x cubed times another x, x to the 4th times another x squared. It's going to be x to the 6th. So the end behavior is what? We know that the degree is x to the 6th. And what's the number in front of this, my x to the 6th going to be? Well, this is going to be positive, positive, positive. So we know that it's going to have a positive number, which if that's the case for the end behavior, if it's an even degree and positive number, it's going to look like this in the end. It's going to go up, right? Because remember, we talked about that. So now that I have everything, let's put it together and generate a graph for this. So where are my x-intercepts? They're at 1, 2, and 5. 5. So 1, 2, 5. And then we know we have a y-intercept where at, we'll call this 10. So I know it's going to go up, and at x equals 1, it has a multiplicity of 2, so it's going to come down and bounce off. Notice how it looks like a parabola. It's going to go up, and it's going to have to turn back around because we have a 0 here, and usually it turns around halfway between your zeros. So it's going to turn back around, and at x equals 2, it's going to, the multiplicity is 1, so it's going to cross, and it's going to be linear, so it's going to look like a line. And then it's going to turn back around. At x equals 5, multiplicity is odd. It's going to cross, but it's going to act like a x cubed graph on it, and then it's going to go up forever. And there's my graph. So notice how I kind of put the pieces together and I graph this. Now, how accurate do our graphs have to be? They don't have to be 100%. As long as they're close enough, that's what we care about. Okay? So let's look at our next example. So for example 5, and you might want to pause this video and graph this on your own. This is what? Negative 2x to the 4th minus x cubed plus 3x squared. So to find my y-intercept, that's easy. Plug in 0 for x, and we get 0. So in fact, that's not only is it a y-intercept, it's also an x-intercept. So to find the x-intercepts, we just take negative 2x to the 4th minus x cubed plus 3x squared. You set it equal to 0. Now we solve by factoring. So factor out an x squared, and we're left with negative 2x squared minus x plus 3. And if I wanted to, I could have factored out a negative just to make that a positive. Let's do that. If I factor out a negative x squared, that becomes positive, positive, negative. Now let's see, does this factor? I think it does, which that factors to what? 2x, x, minus or plus 3 minus 1. That works. 2x squared minus 2x plus 3x minus. Okay, perfect. So what do we notice here? What are my zeros? X equals 0, this one, but it has a multiplicity of 2 because there's 2 of them, so this is a multiplicity of 2. This is going to be what? X equals negative 3/2 if I solve for this with a multiplicity of 1. And then this one is x equals 1 with a multiplicity of 1. Okay, now what's the end behavior? Well, what's the degree? The degree is even, so and the coefficient, so it's negative 2x to the 4th. That's what I'm looking at, right? The degree is even, coefficient is negative, which means it's going to look like that. So now that I have all the information, let's put it together. We have an x-intercept at 0, x-intercept at negative 3/2, x-intercept at 1. And we know that it's going to go down forever after my last x-intercept. Then it's going to go up. It's going to cross at 1 because the multiplicity is 1. It's going to act like a line. It's going to turn back around. At 0, the multiplicity is 2, so it's going to bounce off. It's going to look like a parabola. It's going to go up, and then it's going to have to turn around and come back to negative 3/2. And it's going to cross, and it's going to be more linear because the multiplicity is 1. And then it's going to go down forever because of my end behavior, right? So notice how the end behavior kind of kicks in when? After my first or my last intercepts, my last x-intercepts, okay? So let's do one more example. So for example 6, we're going to say graph p of x equals x cubed minus 2x squared minus 4x plus 8. So to find the y-intercept, that's going to be just, if I plug in 0 for x, I get 8. So 0, 8 is my y-intercept. For the x-intercept, we set this whole thing equal to 0. and we factor. Now for this one, if you notice, I have 4 terms, and not all of them have x's. So we factor by grouping, if you remember. So I'm going to group them. I'm going to say, hey, these two, what do they have in common? An x squared. I'm going to factor out an x squared, which leaves me with x minus 2. These two, what do they have in common? They have a 4 in common, but since this is a negative, I'm also going to factor out the negative. So if I factor out a negative 4, what am I left with? X minus 2. And look at how nice this is. Now look, this and this have what in common? An x minus 2. So let's factor out an x minus 2. And I'm left with an x squared minus 4, because of that's what's left over. And then the x squared minus 4 factors even more. X minus 2, x plus 2 equals 0. So if I move up here, what do you notice I have? I have 2x minus 2, so it's x minus 2 squared. X plus 2 equals 0. So what are my zeros? X equals 2 with a multiplicity of 2. X equals negative 2 with a multiplicity of 1. Now, as far as the end behavior goes, what's my highest degree? It's what? X cubed. The coefficient is positive. It's 1, right? So what do I know? It's going to look like that. It's going to go up to the right, down to the left. So let's graph this. What are my, I have a y-intercept, let's call that 8. I have an x-intercept at negative 2 and at 2. Okay, so what do I know? At x equals negative 2, the multiplicity is 1, so it's going to cross. So it's going to cross like that. It's going to go up, and then it's going to come back down. And then at x equals positive 2, what do I notice? My multiplicity is 2, so it's going to bounce off, act like a parabola, and then go up forever. So notice how with all these pieces we're able to graph these polynomial functions by putting everything together. So this takes care of the notes, and we will spend a few days on this, so just keep at it, and if you have any questions, don't hesitate to reach out to me, and I'll be more than happy to work with you.